The RMS charge radius is a measure of the size of an atomic nucleus, particularly of a proton or a deuteron. It can be measured by the scattering of electrons by the nucleus and also inferred from the effects of finite nuclear size on electron energy levels, as measured in atomic spectra. Definition. The problem of defining a radius for the atomic nucleus is similar to the problem of atomic radius, in that neither atoms nor their nuclei have definite boundaries. However, the nucleus can be modeled as a sphere of positive charge for the interpretation of electron scattering experiments. Because there is no definite boundary to the nucleus, the electrons see a range of cross-sections, for which a mean can be taken. The qualification of RMS arises because it is the nuclear cross-section, proportional to the square of the radius, which is determining for electron scattering. This definition of charge radius can also be applied to composite hadrons such as a proton, neutron, pion, or kaon, that are made up of more than one quark. In the case of an antimatter baryon, and some particles with a net zero electric charge, the composite particle must be modeled as a sphere of negative rather than positive electric charge for the interpretation of electron scattering experiments. In these cases, the square of the charge radius of the particle is defined to be negative, with the same absolute value with units of length squared equal to the positive squared charge radius that it would have had if it was identical in all other respects, but each quark in the particle had the opposite electric charge. It is customary when charge radius takes an imaginary numbered value to report the negative valued square of the charge radius, rather than the charge radius itself, for a particle. The best-known particle with a negative squared charge radius is the neutron. The heuristic explanation for why the squared charge radius of a neutron is negative, despite its overall neutral electric charge, is that this is the case because its negatively charged down quarks are, on average, located in the outer part of the neutron, while its positively charged up quark is, on average, located towards the center of the neutron. This asymmetric distribution of charge within the particle gives rise to a small negative squared charge radius for the particle as a whole. But this is only the simplest of a variety of theoretical models, some of which are more elaborate, that are used to explain this property of a neutron. For deuterons and higher nuclei, it is conventional to distinguish between the scattering charge radius (ρ) and the bound state charge radius (ρ), which includes the Darwin-Foldy term to account for the behavior of the anomalous magnetic moment in an electromagnetic field and which is appropriate for treating spectroscopic data. The two radii related by where μ and md are the masses of the electron and the deuteron respectively, while λc is the Compton wavelength of the electron. For the proton, the two radii are the same. History. The first estimate of a nuclear charge radius was made by Hans Geiger and Ernest Marsden in 1909, under the direction of Ernest Rutherford at the Physical Laboratories of the University of Manchester, UK. The famous experiment involved the scattering of alpha particles by gold foil, with some of the particles being scattered through angles of more than 90 degrees, that is, coming back to the same side of the foil as the alpha source. Rutherford was able to put an upper limit on the radius of the gold nucleus at 34 femtometers. Later studies found an empirical relation between the charge radius and the mass number, A, for heavier nuclei, R0 A1/3, where the empirical constant R0 of 1.2–1.5 fm can be interpreted as the proton radius. This gives a charge radius for the gold nucleus of about 7.5 fm. Modern measurements. Modern direct measurements are based on precision measurements of the atomic energy levels in hydrogen and deuterium, and measurements of scattering of electrons by nuclei. The non-zero size of the nucleus causes a shift in the electronic energy levels, which shows up as a change in the frequency of the spectral lines. Such comparisons are a test of quantum electrodynamics. Since 2002, the proton and deuteron charge radii have been independently refined parameters in the CODATA set of recommended values for physical constants. That is, both scattering data and spectroscopic data are used to determine the recommended values. The 2014 CODATA recommended values are: proton, P equals 0.8751 times 10⁻15 meters, deuteron, ρ equals 2.1413 times 10⁻15 meters. Recent measurement of the Lamb shift in muonic hydrogen indicates a significantly lower value for the proton charge radius. 0.848487000000000000000 0.84087 FM. The reason for this discrepancy is not clear.